Well, thank you, Greg. We really, really appreciate the invitation, and we're delighted to tell you a little bit about this incredible discovery that we've made over the last couple of years. So Tyler and I are going to tag team this talk, so you'll hear from both of us over about the next 15 minutes before we move to the Q&A. So over the last 600 or so million years, through the sort of period of multicellular life on Earth, the diversity of life has increased from that time period to today, from the beginning of multicellular life to the point today. But it's been punctuated by these mass extinctions, and we have 5 of them in the fossil record. So what you see is diversity on the vertical axis and time on the horizontal axis. And those different colors represent different sort of major groups of families throughout Earth's history. And again, anytime there's a dive, there's a mass extinction. The most recent one, the end Cretaceous extinction, of course, is responsible for the extinction of the dinosaurs. But I want you to think about extinctions a little bit and what they mean for the course of life. So on the left-hand side, you see a branching pattern. That's one way that we sort of show diversity. You can imagine this as a diversity or a branching pattern of the diversity of life. And you get an extinction, you get a pruning of that tree, if you will, a clipping. So that red line might be a mass extinction, any number of different causes to cause that mass extinction, sometimes instantaneous, sometimes prolonged. And the things that survive are the starting points for the diversity afterwards. And so everything that you see alive outside today has an ancestor that survived one of the great mass extinctions. So what I want to do is take you back 66 million years ago to the last great mass extinction in Earth's history. We were hit by a space rock about 6-7 miles across, moving at 150,000 miles an hour. It slammed into the Yucatan Peninsula, brought outer space right to the surface of the planet, blew a hole about 100 miles across and 20 miles deep, literally liquefied the surface of the Earth, sent a shockwave from Mexico to Alaska in 5 minutes. And of course, if you were in that shockwave and firestorm, you would have been absolutely toast, as these 2 dinosaurs would have been. In this case, somehow they're preoccupied still fighting, even though there's this giant shockwave coming at them. And all the subsequent effects of this asteroid, including material raining back to the Earth and superheating the atmosphere, changes in the chemistry of the oceans, led to the extinction of the dinosaurs alongside many, many other things. And this moment sort of recalibrates the direction of life 66 million years ago. So we at the Denver Museum of Nature and Science study this time period a lot, the extinction of the dinosaurs and the time afterwards. A lot has been done on what was alive in the last moments, how close they got to that actual extinction event, what caused them to go extinct, who went extinct, and then some on who have survived. But what's been interesting is there's just been this lack of data after the boundary. And so in this nice diagram here, you see all the dinosaur players on the landscape, here in this case in North Dakota and Montana. And then that line represents that extinction point. And above it, there's very, very little data. And there's a number of reasons that the data is limited, but suffice it to say, the data is limited, and yet we know what is alive today, and we can retrace those steps back to that time period. It was a period that was sort of shrouded in mystery. So Tyler and I, as colleagues that work on this time period, became very interested in how life recovered after the last mass extinction. Because of course, knowing something about this tells us something about what's alive and why it's alive on the planet today. So we were looking around the world, across the American West, and really across the globe for places that might preserve this time period. And one of those is right here in our backyard in Colorado. So we live on the Front Range, and just to the east of the Front Range is a pile of rocks that contain the Cretaceous Tertiary or the Cretaceous Paleogene boundary. And so this site here, this is Corral Bluffs, just outside of Colorado Springs. That's Pikes Peak in the distance there. We're just about 5 miles east of downtown, 5 to 10 miles east of downtown Colorado Springs. And these rocks preserve that time right above the boundary.
And of course, this area called Corral Bluffs is not new to scientists. People have been working out there since at least the 1940s. This is a picture from a paper from the Smithsonian's expedition in the early 1940s. Because this is an interval of time that has fascinated scientists for a really, really long time. It's the origin of the modern world. It's such an incredibly important interval of time that scientists have been going to these areas around the world that preserve the Cretaceous-Paleogene boundary to try to squeeze every bit of data from these rocks to try to figure out from how the world originated. And unfortunately, it's notorious for having a really poor fossil record. I've been working in this right after the Cretaceous-Paleogene boundary for about 20 to 25 years, and I can count on one hand how many mammal fossils, mammal jaws I've found prior to this major discovery. So here in my hand is a major, before this discovery, what would have been a major discovery from this interval of time. And you can see these are just fragmentary scraps of a lower jaw. You can maybe see the teeth sticking up in the photo. And this is where our big aha moment happened, where we went from looking for fossils like this, a bit of a needle in a haystack, to looking for concretions. And so here is a concretion. A concretion is just a special type of rock that forms around an organic nucleus. You can think of like a pearl on an oyster shell. And so in this case, you can see the pearl is this beautiful mammal skull that's encased in this ugly, sort of nondescript looking rock. So scientists have been going out to this particular area at Corral Bluffs since at least the 1940s, looking for fossils from this interval of time and basically walking over and kicking these rocks. And again, that was our aha moment when we realized that the fossils were inside of these concretions. And you can see why a lot of people would have walked over them, because they are very, very nondescript. They're just slightly different shaped rocks mixed in with other rocks. But inside these amazing rocks are whole skulls of these mammals. Whereas before we only had fragments of jaws, maybe a partial skull, we now have entire skulls and in some cases entire skeletons. It was amazing the way it happened. We found so many fossils in so little time from this critical interval of time. This is just a small selection of some of the fossils that we found from this interval of time. And in every single case here, this either represents a brand new species of mammal, turtle, or crocodile, or it represents the most complete known specimen from a known species.
So to pull all of this off, we build these big teams of scientists. So we collaborate around the world. And here's just a photo of some of our scientists. We work with graduate students. We work with even undergraduates and high school students. Some of our biggest discoveries were actually made by teenagers in the field because they were out looking for things. And sometimes, that discovery just happens in that moment. So we need that big team of people to pull all these different facets of the science together. So my specialty is fossil plant life. On the left-hand side there, you see a whole bunch of imprints of different types of leaves. And they tell us something about the ancient forest, the leaves of those ancient forests. And then on the right-hand side, you see pollen. So we actually can dissolve rock and extract microscopic fossil pollen. You're looking at things, well, you see a scale bar there for 50 microns up there on the top. And this little diagram in particular is showing you the change in plant life across what is called the Cretaceous-Paleogene boundary. So the bottom being a diverse assemblage of different kinds of pollen types, those pollen types representing a forest, all kinds of a very diverse forest. A moment there in the middle section where the forests are devastated, and what proliferates are ferns, so lots and lots of things that are, they're just taking advantage of all this new ecological space. And then the top, a whole new forest coming back in the Paleogene, that time period after. But again, it takes a team. I'm not a fossil pollen specialist. Our fossil pollen specialist is from France. One of the most tattooed scientists in the world is pretty incredible. And then we draw on all kinds of technology. So we do a lot of community topography work. Here's Tyler working with a technician actually at a vet clinic. So going to the vet clinic on a Friday night when all the patients, the dogs and the cats are gone, and sending our fossils through the CT scanner to produce images like you see there on the right. So on the left is one of these very bizarre early mammal that is now extinct. That line is extinct, a beaver-like animal, and then CT data on the right-hand side. And I draw your attention to the bottom there, that little purple and sort of blue. Those are the ears, the inner ears of that animal that tell us something about the balance and the kind of ecology that it had. We can actually look inside the fossils. But our team of scientists, it ended up being 16 people on this most recent study, but they have all their teams of people working on things. And ultimately, what came together for this study is something that we call the Trifecta of Paleontology. We found fossil vertebrates and fossil plants. Often the chemistry of the rocks don't allow those to be preserved in the same place or in the same beds, and they are both there for a variety of reasons. And then tying that to time. It's not always that straightforward to tell time precisely in a stack of rocks. And so being able to date the rocks precisely, and we do that through a number of geochronologic techniques. And the three things together, these three things together, really allow us to paint a picture of how the modern world emerged from the ashes of the asteroid impact.
Yeah, to have these three things, this trifecta of paleontology from any interval of Earth's history would be pretty incredible. But to have it from this interval right after Earth's mass extinction is like winning the Powerball. I mean, it's incredibly, incredibly lucky to have all of those things. Something that ourselves, as well as many other scientists, have been looking for a really, really long time. So, what does this spectacular fossils? What do they tell us about what happened after this mass extinction? So this is what we knew beforehand, right? We knew that there were dinosaurs going along, and then a giant rock from space fell and wiped out the dinosaurs right at about 66 million years ago. But we didn't know a lot about what happened afterwards. So we worked with, again, a team of scientists. I study the vertebrates, Ian studies the plants. We had worked with a number of other people who worked on figuring out how old our fossils were. They were dating the rocks in which the fossils were found. So we could precisely date every single one of our fossils. And what we found is that we had basically the first 1 million years after Earth's last mass extinction event. And then, of course, I was out there collecting all of these wonderful, wonderfully complete mammal fossils. And there's any number of amazing things that we can do now that we have entire skulls, and in some cases, skeletons. Whereas before, we only had teeth. One of the easiest things we can do with those data are to figure out how big they were. Just how big are these animals? And so that was sort of the lowest hanging fruit, and that's exactly what we did here, is we documented the changes in mammalian body mass across the boundary, and then how quickly did it take for mammals to get big, for Earth to recover. And mass is certainly one metric of recovery. And you can notice that there's a couple of pretty big jumps right here. The largest mammal that's in the latest Cretaceous is about the size of a raccoon. The largest mammal to survive the mass extinction is about the size of a rat. And then you can see there's a couple of big jumps, which I'll talk a little bit more about. And then Ian and his team, they went out and collected over 6,000 plant fossils to really reconstruct what these ecosystems looked like. Ian and his team, as well as a team of people who study pollen. One of our collaborators counted over 37,000 pollen grains to figure out, again, how the forest changed from before the mass extinction through the first 1 million years. And then from the plants, we were able to figure out the temperature. We were able to get plants are a good proxy for temperature. And what we noticed is we found 3 distinct warming intervals after the mass extinction. And what we're able to do then is tie this all together to see how these plant ecosystems were changing alongside the ever-increasing, the larger and larger mammals, and all through that first 1 million years, to paint these really vivid pictures of how Earth changed when the asteroid struck, and how quickly did the Earth recover? And so that's what I'll walk you through here. So this is what Colorado would have looked like, say, 67 million years ago. You had T-Rex, rivers, full of turtles. A lot of other feathered dinosaurs would have been roaming around. And then you had the asteroid strike, right? And this is the biologic reset button. It completely changes the course of life on Earth. If it hadn't been for this giant asteroid, dinosaurs would still be around and we would not be here today. This is what Colorado would have looked like within the first maybe 100 to a few hundred years after the mass extinction. One of the first things that bounces back are ferns. So you would have had the world blanketed by ferns. And in the understory of these ferns, you would have the largest mammal to survive the mass extinction here in this illustration. That's, again, only about the size of a rat. And then next to it, just for juxtaposition, we have the largest animal, period, that survives the mass extinction, and that's a large soft-shell turtle. Then the world would have changed to a world dominated by these palm forests. So this would have been a very unusual forest with very low diversity, not a whole lot of types of plants, but there would have been a lot of palm trees. And in the understory of this palm forest, you would have the first big jump in body size. And that is this animal here, about the size of a raccoon. This is about 100,000 years after that mass extinction. And this is a mammal that's about the same size as the mammals before the mass extinction. So it takes approximately 100,000 years to achieve that same body size as before the mass extinction for mammals. And then the next thing that we noticed is a world that we dubbed the pecan pie world. And that's because at this moment in time, this is about 300,000 years after the mass extinction, the forests are really starting to come back in terms of diversity. And one of the key groups that is diversifying during this interval is the walnut family, which includes the pecan tree. And at that exact same interval, we see a major jump in body size in mammals. So this is an animal here that's about the size of a pig maybe, and this is 30 times larger than the mammals that survived the mass extinction. So it's a major, major jump in terms of relative of body size. And then lastly, we have, I think, my favorite world. Again, the forests are starting to really start to bounce back. This is about 700,000 years after the mass extinction. We found the world's oldest bean pod. So when we dubbed that the protein bar world, because beans are rich in protein. And at this exact same interval of time, when we have these beans, these legumes, entering into the world, we see yet another major jump in body size. And here we have an animal that's about the size of a wolf. This is 100 times larger than the mammals that survived the mass extinction. And mammals won't see a comparable jump in body size for another 30 million years. So it just shows you how quickly the world really rebounded. 700,000 years is pretty fast in terms of geologic time. So we're really excited to be able to announce this discovery to the world. A couple of months ago, we made this discovery in 2016, but it took a while for us to build the team of scientists, to gather all of the data, to really pull everything together. And so a team of 16 scientists, we published this in the scientific journal called Science. We collaborated with a number of filmmakers at the Howard Hughes Medical Institute to create this wonderful documentary called Rise of the Mammals, which you can stream online now on Nova. And then we worked with a number of museum professionals to put together this amazing exhibit that we have on display now at the Denver Museum of Nature and Science. So this really was this team building exercise of not only the scientists, but then pulling in the filmmakers to create this wonderful film, as well as museum professionals to really sort of broadcast this major scientific discovery. And with that, I'm just going to lastly play a trailer from the documentary, which I think is a pretty good summary of our findings. It's a really bad time for life on Earth.
I mean, you could go your entire career and not find a skull from this time period. That's how rare they are.
They're excruciatingly hard to find.
There's just nothing like picking up something and finding out it's something amazing.
It was crazy the way it happened.
Bam! We hit it big. I just found a mammal skull.
It was like opening a door into a new world.
We want to build up a picture of how life evolved in this period.
Some things survive, right? Including some of our earliest ancestors.
Over the last 66 million years, mammals evolved in incredible diversity of forms.
That moment of rapid mammal evolution is effectively the trigger to our existence here on planet Earth.
So anyway, well, thanks. That's pretty amazing. And I'm sure I could sit here asking questions for hours and we wouldn't be barely scratching the surface. But I do have a few questions prepared and then we'll be opening up for the live Q&A. So I'm going to start with a pretty, what I hope is a obvious question that, you described the mass extinction at the end of the Cretaceous, which probably many of us had heard of before this talk today when the dinosaurs went extinct. Obviously, those you showed, there were survivors. So what was it that allowed these plants and animals to survive the asteroid when others didn't? Was it dumb luck or was there something more involved?
Well, maybe I'll talk about a little bit about the plants and you talk about the animals. So certainly there is an element of luck involved, I would imagine, though we are continuing to probe these data sets to see if we can figure out just the answer to that very question. So for instance, in the plants, one of the things we've noticed is that things that are deciduous survive better than things that aren't. And we can tell that based on the mass of these leaves. And we estimate the mass of an ancient leaf by the width of its petiole, its stem, compared to the area of its leaf. And so with that proxy, we're able to show that things that survive the extinction probably were deciduousness. And you can imagine the environmental effects that might happen at an asteroid impact. You blot out the sun, it gets cold. And so if you have the ability to drop your leaves, you probably are going to have a better chance of surviving. So that's one aspect of why certain kinds of plants survived.
Yeah, and I think in terms of the vertebrates, there's a number of selection filters going on at the Cretaceous-Paleogene boundary. The biggest thing is just size. So small animals do much better across this boundary than the large animals. All big dinosaurs go extinct. Pretty much all large animals, period, go extinct at this interval of time. Another thing is where you lived. And that's if you lived underground or underwater, you were buffered from that thermal pulse from the asteroid impact. And so if you were able to buffer yourself from that initial thermal pulse by living underground or underwater, then you had a much higher chance of surviving. And then the last thing I would say, is diet. If you were a specialist specializing in eating just meat or in plants, those animals do not do very well across this boundary. But if you were an animal that ate detritus or just dead plant matter or just had a very generalized diet, you do much better. So the real winners of this mass extinction are turtles and crocodiles because they're small, they're aquatic, and they have a very generalized diet. And if you only looked at turtles, you would not even know there was a mass extinction across this interval. Whereas 90% of mammals go extinct, 90+% of birds go extinct. So pretty devastating across the animal kingdom.
All right, very interesting. And so would you say the ancestor to those mammals whose fossils you found at Corral Bluffs, were most of them subterranean, or do you know that?
We don't know that, but that's a very good hypothesis. I mean, and I would expect that they're either living underwater or underground. But we don't yet have the fossils from right after that interval to determine that.
Well, that's work to be done. Yeah. So is there any reason particularly why we found these fossils where we did, down by Colorado Springs? What was special about that area? Or was it, again, just dumb luck?
There are a number of geological factors of why there are fossils down there. Importantly, the Rocky Mountains are being formed at about that time. The Rocky Mountains that we enjoy today are uplifting. It's really the second time they're uplifted. So they were eroded flat and then they were uplifting again. And anytime you uplift mountains, you erode them and you make depressions in front of them. It's just a balance problem on the surface of the earth. But those depressions fill up with sediment, all the mud and sand and that kind of material that comes down in those rivers. And that buries animal and plant life and creates fossils. There's something interesting about the chemistry of these rocks. We don't know the answer to that. It's one of the areas that we're working on right now, but the preservation that led to these fossils, whereas we've never found fossils this well preserved from this time period, the mineralogy is different, the chemistry is different. There's something going on that's allowing these things to be preserved in addition to being buried. So.
And then I think in terms of just the overall discovery, I think there is always a bit of luck involved. We try to increase our odds of finding the fossils, especially from this interval of time, by just placing ourselves around the world where these types of rocks are exposed. We've sort of a numbers game. Eventually, we figured we would hit it big and find fossils from this critical interval. But I never would have guessed that we would find it essentially in Colorado Springs, that this major discovery would happen in the city of Colorado Springs. I always thought it would happen up where I grew up in North Dakota or Montana, because there's vast exposures up there, or in another part of the world. But yet here it was, this major discovery in our backyard. Pretty incredible.
Yeah, that is pretty awesome. Is there, from what you learned at this exposure from the chemistry and the concretions and all that, are there now other places in the world where you or other people are saying, oh, well, maybe we should be looking more closely at these rocks?
Absolutely. I mean, I think Mother Nature tends to repeat herself, and it's only a matter of time before somebody finds a similar deposit. And so Ian and I are currently looking elsewhere around the world, or at least we're hoping to go elsewhere to look for similar deposits, but they have to be out there. This would be so bizarre if this was just a one-off.
Right. And kind of following up from that, are there other research directions that you hope other people working in these fields will use these fossils to follow up on?
Yeah, absolutely. So not only are we taking it in a whole number of directions, but we hope other people will key in on some of the things that we've hinted at with this record. One of the things that we've noticed in this record was the intimate sort of tie between the animal, the plant records, and climate. So showing that pulses in climate are driving probably plant migration and maybe even evolution, and that in turn driving animal evolution. So there's any number of implications that other groups might focus on, whether it be on land or in marine settings, to tell or to investigate those claims, right? So we just have one spot on the planet where we've been able to put this story together. Are the same dynamics operating on the other side of the planet? Are they operating in the ocean? We don't know. So we hope other teams pick up those threads.
Yeah, I think in our own team, we're taking this research in any number of directions right now. So Ian talked a little bit about computer tomography scans. So we're finding all these wonderfully complete skulls of these mammals. We're sending them off to get CT scanned, and then from that we're able to look at their brains and their inner ears and all of this anatomy that we previously did not have access to. So we're looking at the early evolution of the placental mammal brain. That's one of the big things. It's one of the things that defines mammals in general, and particularly placental mammals, as our giant heads and giant brains. So we're looking at how that particular suite of characters originated. There's just any number of amazing research opportunities that we're sort of spinning off from this. And we get email, what's great about it is we get emails almost every week from scientists around the world who are interested in collaborating. And it's great that we're able to continue to build our team of scientists. Because again, we are only specialists in our certain little area. And so we're really trying to leverage these fossils and to tell as big of a story as we possibly can.
So what's some of the technical challenges you face here, whether it's in doing the work or sharing out the results?
Yeah, that's great. There are so many. So, I mean, we spend most of our time dealing with technical challenges, as I'm sure you guys probably have similar experiences. On the side of the fossil plants and the whole plant world, we're looking at, again, the chemistry of the rocks, but we look at isotopic tracers of essentially nutrients or different carbon, nitrogen, that kind of thing in the soils. And so those things need to get processed and measured in mass specs. And sometimes the sample size is so small, we're pushing the edge of what we can actually measure, or just the density of those molecules or isotopes in this case aren't that dense in our record. So that might be one part. Preparation of fossils is a really big thing. So certainly in Tyler's world, prepping those fossils out of those concretions is a big deal. Certainly in the plant world, getting the plants out of the rocks can be tricky. So that's one of our technical challenges. What would you add to that?
I think another one is just we have so much data. We're just choking on the data. So one of the things that we did is we collaborated with the U.S. Geological Survey to fly drones over our area to create great photogrammetry models of our research area, our field area, and then from that we can help date the fossils that we're finding, because everything about what we're doing is we have to put it into a timeline context. So it's so incredibly important. But then we get just these massive amounts of data back that we just really don't know how to handle, or at least you and I don't know
That's right.
how to deal with that.
Right.
And so we're choking on these data sets. And what I would love to have is a Google Earth interface for these amazing data sets that we have, because I use Google Earth pretty much every day, all the time when I'm out in the field doing, when I'm going to do field work in new areas. So anyway, that's...
If you want to help us, let us know, please.
Yeah, I don't know if we've got anyone on Google Earth here today, but make sure if you know someone on Google Earth, put them in touch. And so that kind of leads to another question. You know, you mentioned when you were talking that you had people from all over the world, and so what's that like? I mean, you've got scientists from different countries and speaking different languages with different backgrounds. What was that like?
It's a lot of fun. I mean, it's so great. I mean, it not only enriches the science, but it enriches our lives. I mean, we create these wonderful friendships with these scientists from around the world, which I think is fantastic. And then just in terms of the project itself, I mean, it really just magnified the results by bringing on all of these specialists, and really weaving all of those specialties together to really paint these pictures of how life recovered after the mass extinction.
Right, and just a question I have, curiosity-wise, how many folks are there working on this around the world, working on this particular time interval, you know, in terms of paleontology and paleobotany? Do you have an idea about that?
There are not that many paleobotanists, it turns out. We're a pretty rare breed of scientists. There's probably about 500, maybe 1,000 paleobotanists. There are some huge groups in China that are growing. There's a whole museum dedicated to paleobotany. One of my colleagues runs a museum there that he's training students like crazy, which is amazing. It's awesome. So on the topic of the KT boundary, I mean, it's hundreds, if not thousands of scientists. Just last year, there were multiple groups publishing in the top academic journals on this very problem. And so we added a piece to that story, and an unknown piece, right? There was a piece that nobody had ever seen on land. So I think we have a new cog in the wheel that's quite important, but it is literally hundreds of scientists out there.
Yeah, I would say thousands. I mean, I think it's one of Earth's most interesting interval of times. I mean, clearly I'm biased, but this interval of time right here combines space with a giant asteroid, a mass extinction, dinosaurs, and giant volcanoes. Because that's the other thing which we didn't talk about here is that the other potential cause of the mass extinction is these giant volcanoes going off in India. It's going on right at this same interval of time. It's definitely playing into our story. So you have these four amazing things all colliding at this interval at 66 million years ago. So it draws on a number of I think, subdisciplines. And it seems like every couple of weeks, months, there's a big paper that comes out on the Cretaceous-Paleogene mass extinction.
Very cool. And before I open up to Q&A, I'm going to ask one more question. You mentioned that there were undergraduates and high school students and everybody else involved with this project. Are there ways for people to get involved today, whether in terms of volunteer opportunities, or is it even possible just to go visit, or is that all roped off and locked down?
Yeah. You can go visit. So the city of Colorado Springs is providing tours for just interested public to go and visit the site itself. They run, I think, every Saturday based on demand. You get in touch with what's called TOPS in Colorado Springs. Can't exactly remember what that acronym stands for, but it's part of the Trails and Open Space program, something like that. So if you want to see the actual rocks from whence these fossils came, you can do that. In terms of getting involved at the museum, we have one of the most vibrant volunteer programs in the world. We have basically 2,000 volunteers at the museum operating in all aspects of the museum. About 800 of those work in the sciences. So either working on collections, working on one of our prep labs, and even some people take it to the point where they're publishing papers with us. It depends on how much time you want. If you want to completely recreate your graduate school experience, you can come be a graduate student with us. We would love to have you. So yes, plenty of opportunity to be involved.
Come dig with us and we'll put your big brains to work.
That's right. Yeah.
Hi there. Thank you for coming to visit us today. I guess it's almost like a two-part question. I guess the first one is why the concretions at this period of time and not before, or was it, and it's just sheer numbers that you're only finding the concretions now? I guess that's the whole question, is why did it occur that way?
Yeah, why concretions and why this interval of time? We do think that these concretions extend deeper in time at this interval of time. So they are around when dinosaurs, they're forming around the dinosaurs as well. Why they form where they do is, like Ian was saying, is a very interesting question. Like, that's one of the lowest hanging fruit questions that we have right now that we're currently trying to address, because we seem to only find these concretions in areas that are closer to the mountains. So if you go to my home area up in North Dakota, Montana, vast exposures of this exact same interval of time, there are no concretions. You even go further out into the Denver basins, like south of Strasburg, we have that exact same interval of time preserved, no concretions. So there seems to be something special about being close to the mountains. Maybe that has to do with rapid burial. There's likely a number of things going on there, but certainly rapid burial is one thing that plays into it, and then a very specific type of groundwater chemistry. And again, I don't think it's going to be just unique to this area, this part of the world. There are other areas that were close to the mountains 65 million years ago that very well could have concretions preserved as well.
And to add to that, in marine sediments and ocean sediments, concretions are very common. So if you were a fossil buff, or anybody's a fossil buff in the audience, you may have actually cracked open concretions to find ammonites and shells and other kinds of things like that. And in fact, paleontologists look for concretions specifically to find fossils in marine settings. But this is a terrestrial setting and essentially unheard of at this point. There are a few other examples at different time periods, but many tens to hundreds of millions of years from this moment in time.
It looks like the strata that, from the pictures you showed from the field, it looks like it's shaly, very soft stuff. You don't have hard strata for dating purposes. How confident are you that these are actually coming from that point in time, as opposed to aggregation that's coming down off the Rockies, and and then dating all of that stuff, given the lack of hard strata?
I think that's a great question. So a lot of these fossils are found, what we call, they're found in situ. So they're sticking right out in the sediment itself, in the shale or the mudstone sediment, or in the river sandstone sediment. So for those particular fossils, we can be very, very confident that they're in situ, and we can be very confident on the age of those fossils. One of the good things about concretions is that they form around the bodies, but then they can roll down the hill and still be preserved really well, which is not oftentimes the case when you're finding those fragments, like those jaws that I was showing you. The downside is, to your point exactly, how can we be sure on how confident can we be on the dating? And there we put in our data sets that they were not found in situ, and they're therefore more of an approximation. But we're still dealing with probably plus or minus 50,000 years, because they can roll, but they can't roll that far, if you know what I mean.
And we can't date the concretion itself, so we have to date the rocks in which it's contained. So once it rolls out of its context, that's where the air gets inserted into the problem.
Hi, this is a distraction, but is the latest thinking that T-Rexes have duckbills?
Well, no. No. I mean, there was a paper that came out, I think in 2016, that put some sort of a covering on the front of the snout of T-Rex, which is, that was based on the vascularity of the maxilla itself. So that idea has been proposed, and our artists just chose to go with that. So I don't. But to say that's definitive, that's even the feathers, and so that the same thing. We know that the cousin of T-Rex that they're finding in China is feathered when it was an adult, but adult T-Rexes likely did not have feathers. They may have had feathers when they were small, but likely lost them when they got older. But this. Sorry?
Giant ducks could be terrifying.
Absolutely,
well, for sure. I wouldn't want to get eaten by that either.
Yeah.
So is it possible to find plant material which is so well preserved that you can grow them?
That we can clone them?
Grow them?
I'm sorry.
Grow them.
Grow them. Yeah, sorry. So yes, to a degree, but not at this age. So the oldest viable seeds are about 30,000 years old. They've been found in northern Russia, Siberia, in the permafrost, and they've managed to grow these little wildflowers from seeds that they found there. Normally the genetic material in the seed degrades very quickly. DNA is phosphorus based in part, and that it just falls apart very quickly for a whole variety of reasons. But anything that's sort of viable from a growing standpoint is gone.
Hi, I'm curious about the crocodiles and the turtles that also survived their extinction. Do they also see like an increase in growth in size as the mammals did? Or if they didn't, what was the reason for that?
It's a good question. We don't really see that big of a jump in body size. And I think it's basically because they did well across that boundary. They didn't really adapt and grow into these different ecological niches that were opened up. That's one idea. Another idea is that they have a slower rate of molecular evolution compared to mammals and compared to birds. Those were the two groups that really diversified and really filled those niches very, very quickly, birds and mammals, because they suffered mass extinction. The ones that survived were really, really small. If you're small, you have a faster rate of molecular evolution compared to larger animals. And if you're an endotherm compared to an ectotherm like turtles and crocs, you have a faster rate of molecular evolution. So I think those two groups, mammals and birds, just really, really quickly diversified afterwards. And turtles and crocs is just sort of business as usual across the boundary. Big rock falls, and they just keep chugging away.
When you say molecular evolution, is that like the rate at which mutations occur per
That's
generation?
Right. Yep.
Okay.
Yep. Yeah, there's been some interesting recent studies on that, looking at the impact of the changes in rates across this interval of time. One of the more interesting studies that I found was was just the size. So we've always known for a long time that it was small animals that survived this mass extinction. And then more recently, we've realized that it's smaller animals that have a higher reproductive rate and therefore faster rate of molecular evolution, and the impacts of that on diversification. That plays into it. That definitely plays into the rate of molecular evolution. Yeah.
Why do you think dinosaurs didn't come back after the boundary, after the mass extinction? Right, like mammals did. Why didn't small birds that we think are evolved from dinosaurs, why didn't they come back into things like T-Rex and Triceratops and Brontosauruses?
It's a good question. I mean, on the one hand, birds are dinosaurs. So they are still with us today, and there's something like 9,000 species today. So they are doing quite well. But they're not big, and I think it's just those developmental pathways, those genes, were sort of snuffed out at the KPG boundary. And it's not to say that it won't, a couple million years from now, 50 million years from now.
Yeah. And extinctions do this, right? They clip out whole lifestyles, ecologies, that kind of thing. And so, and extinction's final too. One of the things we think about today is going through what is arguably the 6th mass extinction. It's good to remember that while life is very resilient, our study shows that life comes back quickly and it is quite resilient. It is a different direction, right? So whole lifestyles are gone. And that is a consequence of extinction. Unless we can figure out de-extinction. Of course, that gets in the news a lot.
CRISPR.
Yeah, that's right. Yeah.
The temperature changes that you were correlating to size changes, were those modeled from the plant samples, or are those from like computer models of the climate?
Yeah, so the temperature changes do come from the plant record. So it turns out that there's a whole variety of proxies based on plants and a number of other things that you can get at past temperature. They're all proxies and they all have their error bars, and of course it gets sketchier the further back in time you get. But the basic proxy that we used, and it's been the scientists have used for a long time, is that there's a relationship wherein if you take all the trees and a sort of standard plot size, a couple of hectares, and you measure those species that have teeth on their leaves and those species that are smooth, that correlates with the annual temperature in which they grow. And teeth have a variety of functions related to growth speed, photosynthetic rate, transpiration. And so having teeth is very advantageous in cooler climates, but they're also involved in releasing water. And plants don't have the ability to pump water and photosynthate around their bodies. So they're in balance, so they're balancing themselves. You go to the tropics, it's mostly smooth margin leaves. They don't need that adaptation. You go further north where it's cooler, they're mostly toothed. And so in the fossil record, we can go collect a big chunk of several thousand leaves out of a hole on the side of the hill, separate them all into species, count the species with teeth, those without, and relate them using a proxy base, based on modern floras that we have today. So, and that's one of many, many techniques. And what we were very excited to find in our study was that our temperature pulses lined up with other ones from other parts of the world using other proxies. So that gave us a lot more faith that we were recording real events.
So we talked about ferns, but how about wooden plants? Did they appear after that, or were they already there?
Yeah, wood evolves many hundreds of millions of years ago. The first trees are about 350 to 380 million years old. And it actually evolves independently in different groups, woodiness, if you will. Certainly across the boundary, things that had, again, quick growth cycles, the things that were herbaceous probably did better, but many woody plants survived as well. Trees and plants in general are in some ways better at surviving an extinction event like this, an extrinsic, huge space rock blowing up the surface of the planet kind of thing. Because plants can clone themselves, certain plants can, not all, but they can come back from rootstocks. So even if their trees are blown down, they might sprout again from the roots themselves, or banks of seeds and that kind of thing that can lay dormant for many years. So again, those extinction dynamics are a little bit different than what Tyler described about how the mammals and other animals survived the extinction. Plants just operate a little bit differently. But there were woody plants beforehand, and there were woody plants quickly afterwards, too.
All right. Well, I believe we've come to the end of our time. It's just now 2 o'clock. So please, one more round of applause for Dr. Tyler Lyson, Dr. Ian Miller.